To do perturbation theory with Dirac fields, we still need to prove the Wick theorem. And to prove the Wick theorem, we can also use the path integral formalism. So let's start discussing the path integral formalism for fermionic fields. Now, one problem we will be having when we are dealing with the path integral of the fermionic fields is that when we were deriving the path integral, we defined states, let's just call them phi, such that when we acted on these states by our fields, let me just put the dagger over our fields to denote that they are actually operators. This is actually equal to phi of y, phi of x. And here these phi of y and phi of x are just functions of position. And this is also equal to phi of x, phi of y. So at least for these fields, phi dagger of, okay, so this is phi dagger of x, phi dagger of y acting on these fields phi. So let's just say that they are commuting objects. And we see that, okay, so this is fine. But when we have fermionic degrees of freedom, you see, if we have anti-commutation relations, on one hand we have this is equal to minus psi bar of x, psi hat of x, psi hat of y acting on our state. The left hand side will be psi of y, psi of x. The right hand side will be, if they are just psi of y and psi of x are just numbered, the right hand side will be psi of x, psi of y. Now we have a problem. Because if these are just like ordinary functions, just like in the case of the scalar fields, they should anti-commute. So psi of y, psi of x should be equal to minus psi of x and psi of y. If they are ordinary numbers, they should be 0. So this cannot be satisfied for ordinary numbers. But we need to define something else. And that something else, we will need to define some numbers that anti-commute. They are not operators. They are not operators like our fields. They're just numbers. But these numbers have the strange property that they anti-commute with each other. Such numbers are called the Grassmannian numbers. Let's say that we have a set of such numbers, eta I, eta 1, eta 2, eta 3, etc. And then they satisfy the condition that eta I, eta j is equal to minus eta j, eta I. So if we define such numbers, then these fields, when these fields act on these numbers, on these states, their eigenvalues will be just Grassmannian numbers. And since Grassmannian numbers anti-commute by definition, so this property is automatically satisfied. Now, of course, since we are just inventing these numbers, we have to define some of their properties. For example, this automatically implies that any Grassmannian number squared is actually 0. Well, this is something we had also seen in the case of the annihilation and creation operators. If you just take the square of the creation operator for fermions, it was just 0. And what else we need? We need to know how to define functions of them. Well, if you have any function, let's say f of eta, any sufficiently smooth function, we can make a Taylor expansion. So this will be f0 plus f1 eta plus f2 eta squared. This is just take this as a Taylor expansion. But now, since eta is a Grassmannian number, eta squared will be 0. So this any function of these Grassmannian numbers is just actually a linear function of the Grassmannian number. Here f0 and f1, they just can be any complex number. And what else we will need? In the case of the fermionic degrees of freedom, we were taking their dagger, and hence we should take the complex conjugate. Now what is usually done is we define two sets of Grassmannian numbers. Let's say eta 1 up to eta n, and eta n plus 1 up to eta n, eta 2n. N can be just any number, and eta I star is just defined as the other Grassmannian number, which is shifted by n. So this is the definition, and hence eta and eta star, they also anti-commute. Now, of course, if you have more than one functions of more than one Grassmannian number, you have the corresponding Taylor expansion, eta 1, eta 2, etc. So this will be, let's say, f0 plus fi eta I plus fij eta I eta j plus etc. And these fi, since Grassmannian numbers anti-commute, fij is equal to minus fij. Now to go to the path integrals, we need to also remember the path integral for the scalar fields was an integral over the eigenvalues of the fields of some function. Now we need to, since the eigenvalues now are Grassmannian variables, we need to also define what the integrals are. Now on one hand we have the eta. Now this is just like the normalization of these eta, if you think of it as some kind of a wave function. So we will be normalizing this integral to 1. Now at the same time we would like to have a translational symmetry, meaning that the eta should be equal to the eta plus a being some other Grassmannian number. But this tells us that the integral of the eta should be 0. So these are, keep in mind that these are just consistent definitions of the Grassmannian numbers. Now if you look at the integral of some function of the Grassmannian variables, this will be equal to the eta f0 plus f1 of eta. This is just f1 of the, this is just f1, because f0 is a constant taken out of the integral. We are left with the eta integral, which is 0. f1 taken out of the integral, we are left with the integral of eta, and which is just 1. So this integral is just 1. Now we can have let's look at the Gaussian integrals. The eta. Now the Gaussian integral of a single variable just doesn't exist. You see the eta minus a eta squared. Now this is the Gaussian integral. This is just the eta squared is 0. So this is just the exponent is 1. This is 0. Now we can have more than one Gaussian variable. Let's say we have the eta 1, the eta 2, the exponent of, let's say, eta 1, eta 2, 0, 0, well, let's say a, b, c, and minus c, eta 1, eta 2. This will be equal to the eta 1, the eta 2 exponent. If you write this matrix element out explicitly, this will be, let me put a minus sign, minus a eta 1 squared minus b eta 2 squared minus 2c eta 1 eta 2. Now note that this is anti-symmetric because it will be mainly due to this property over here. Fij should be minus Fij. And again, keep in mind that these are just the A and B. We don't really even need to have them. They will just be 0. So the A and B do not contribute because eta squared is just 0. So we can just set this to 0 to start with. So here we have a symmetrical matrix. And if we set them 0, these terms are also absent. They will not contribute to anything anyway. Now let's take the integral, the eta 1, the eta 2, exponent. Now we can use the Taylor expansion of the exponent. This will be 1 minus 2c eta 1 eta 2. Note that the higher order terms do not exist, so this is exact, because higher order terms will include eta 1 squared, eta 2 squared, which will be equal to, you see, 1 integral of eta 2 will give me 0. So it's minus 2c the eta 1, the eta 2. Let me exchange their position. So that will bring me another minus sign. So this is plus eta 2, eta 1. Now the eta 2 integral is 1. What we are left with is just the integral of eta 1 over eta 1. That is also 1. So this is equal to 2c. And similarly, you can just evaluate other integrals. Now, we also will need the derivatives. Well, the derivative of eta with respect to eta will again be 1. And derivative of 1 with respect to eta will be 0. Well, note that these are just like the integrals. Derivative of eta is 1, so is the integral of eta. Derivative of 1 is 0, so is the integral of 1. And hence this derivative operation for Grassmannian variables is actually equal to the integration operation for the Grassmannian variables. Now, of course, when we are dealing with path integrals, we don't have a single Grassmannian number. We will have eta of x. So essentially, this is a Grassmann number valued function or field. You see, when we were talking about the functions phi of x, this function, what it does is, if you just put a position over here, it gives you a real number or a complex number, depending on whether this is a real or a complex field. Well, similarly, this function over here, when you put a position over here, when you give it a position, it just returns a Grassmannian number to you. So that is why it's called a Grassmann number valued function. So that is essentially the basics of the Grassmannian path integrals. And in fact, you can just identify the path integral. The path integral for, let's write it as z of fermionic degrees of freedom will be the integral over psi and the measure over psi and psi bar. These are essentially the complex conjugates of e to the power minus is, where these psi and psi bar are nothing but Grassmannian numbers, Grassmannian number valued functions. We won't be needing to evaluate this path integral explicitly, but we will still use it to calculate, to prove the Wick's theorem.